Welcome to my talk, which describes today, or perhaps more of the motivation with some discussion of a RISC-V chip for mobile DNA sequencing. Okay, so just a nutshell of the presentation today. So the people I'm working with were interested in creating an ASIC essentially for embedded molecular measurements. The molecules that we'd like to measure right now are DNA. And we're planning a RISC-V based system on chip to do this. In particular, a rocket chip instantiation of the RISC-V ISA with a hardware accelerator for certain aspects of molecular measurement. And actually, that's a process that we're in the middle of right now, and hoping to have a submission late this year. And in the spirit of today's meeting, there's a lot of open source stuff that goes into here, besides just obviously RISC-V and the ISA, and certainly the architectures that have been published by a number of groups. The documentation is probably not too bad, but we're still having a bit of a hard time working through it. That's kind of, I guess, a little reminder for myself. That's open source stuff perhaps could be a mystery if you don't have, to begin with, if you don't have people that know how to read between the lines of whatever information it is that's published out there. Okay, so just a little bit of a background on what we're looking at. And this is, there's some simple ways to measure certain molecules out now. It's actually been an idea that's been worked on for decades and has recently emerged as a practical way of actually building DNA measurement products that you can ship. So the idea involves simply making your molecule go through a little hole. The hole is often another molecule, which are referred to as a nanopore. And in the process of this molecule, the DNA specifically here, going through that hole, given the right setup, electrical setup around this sensor, you can gather real-time measurements indicative of the structure of that molecule. And the scales of these signals are given to you here. Peak to peak, you're looking at a small current of about 100 picoamps with events occurring at about 10 millisecond time scales, individual events. And even getting and processing this current is extremely difficult. So besides probably the greatest innovation of this technology was the realization of those sensors. Substantial genetic engineering was applied to actually create them, or at least modify them from their naturally occurring versions. But close to equally important for the practical application of these sensors has been the development of semiconductors that could sense that small current, amplify it and digitize it for ensuing digital signal processors to compute on. So this is that's also work that we're involved in. This is just an example of a readout chip that we have just recently completed for this type of work. But this is mixed signal analog stuff. Our focus here is on digital RISC-V stuff. And to give you a bit more of a physical appreciation for what's going on here, you know, it's the beauty of these sensors is that you can pack them very closely in a small area. So what this picture on the upper left is just showing is the array of sensors embedded. They're much smaller than these circles. These are kind of pools that hold an individual sensor through which any one molecule can go through. So you can very densely pack these to create the opportunity to measure a lot of DNA in a short amount of time, because these things are also fast. So I thought that from the company's website that works on these stuff, this was quite an interesting video that helps give an exciting sense of what's going on here. You know, you've got those nanopores and also other molecules engineered to help ferry the molecule through. You could see this, the DNA surrounded by a cloud of ions, the current whose flow is disrupted, and then producing a stepwise like waveform, ideally, that is a signature of the molecule that you had just measured. In this particular picture, you could, at least the way it's shown here, the molecule is just kind of sitting still inside of this molecular support membrane. It kind of looks like a bunch of spaghetti. In an actual, room temperature implementation, this thing is moving around. This molecule here is rapidly zipping around all over the place. So there's quite a bit of movement happening, and hence the signal that's produced is nowhere near as clean looking as this illustration is showing, but it conveys the basic idea that, in essence, you can almost view these things as just a digital detector, almost something equivalent to an antenna. Oops. So the package within which these sensors can be placed is shown here. That array that I had shown in the previous slide is really just localized in this little section. So within about a centimeter square area, you can pack 500. You can pack many more than that, but right at the moment, that chip that I showed earlier, the measurement chip, is kind of the limiter here. At least you can pack 500 readout channels within this area, and hence match the sensors to each of the channels that your readout chip can afford. And then this thing called the flow cell is plugged in to the rest of the device, where the remainder of the electronics and communications hardware is housed. And you could see these numbers convey the scale to which these DNA measurement machines have reduced the size of this technology. I mean, commodity DNA sequencers are easily 1,000 times bigger than this by volume. And as far as the way they currently work, someone would come in with a pipette that carries your source material, and there's a little opening within this flow cell that they would just squeeze the liquid in which the DNA is floating, and that would be guided by some microchannels towards this active array area. Other electronics not shown here would establish a voltage across this entire section of sensors and induce the currents to flow that are then disrupted by the molecules. So these things, they're small, but they can measure quite a lot. So ideally, for one of these little guys, they could do about 1/4 of a human genome per hour. So as a kind of a relevant reference point today, that would be about 25,000 coronavirus genomes per hour that this thing could process. That's if all 500 channels are just continuously humming. That's realistically doesn't happen. So it's about 2 times slower than this, so about 0.1 human genomes per hour. It can effectively measure it if you're using it well. The power consumption of this unit is also very small, only 1 watt, and currently this structure costs $1,000. And the sensing scheme is not only limited to these tiny portable devices. It can run on industrial strength units as well. So for example, another device from that same company. It's about 100 times bigger by volume, and altogether about 550 times faster, and is 2 kilowatts, and a lot more expensive, but just demonstrates the range of, I guess, molecular measurement needs that this sensing technology can be applied. With all of that measurement, there's also a lot of data that's generated by these small devices. So if you plug them in and you're filling them with DNA, they'll be pumping out about 10 gigabytes per hour. So roughly equivalent to about 3 high-definition Netflix streams. And there isn't any processing here inside of this box to deal with that data. Really only analog and USB 3 chips are within here, and there's a Spartan FPGA inside of here as well, I think. All of that data is just flying off to an attached computing device, which isn't there just to store those measurements. What you want this computing device to do is a bunch of signal processing to actually tell you what those measurements mean. And the point of our work is to try to transfer as much relevant computing from this machine and into the box itself. So we would, besides whatever existing electronics is present within this little box, we would like to add some other chip that helps it understand what it is that it's measuring, and then perhaps make better choices about its actions, or inform users about the measurements that they're getting without the need for bulky computing. So we anticipate that the ability to place heavy-duty computational power within this box could broaden the applications of this unit. First, to help extend its already demonstrated utility in field genomics. So here you see an example of somebody ostensibly doing some DNA sequencing out in the field. A laptop is sufficient for perhaps whatever work that is required there. But the idea is that you could perhaps scale this to much greater levels if your computing was increased and miniaturized at the same time. So that would perhaps empower things like the ability to do pervasive sensing on a molecular level, things like water monitoring, and even new IT technology. So this just refers to some ongoing work where there's an interest in using DNA as the storage medium for just traditional data, at least for long-term backup. And there's people that make an economic and technological case for this. So in that type of application, essentially sequencing is the way that you would read data out from your data storage device. So the faster that you can do that for less cost would be beneficial. Okay, so specifically what we would like to do is a bioinformatic procedure called base calling, which is essentially just current to text conversion. It's also rather similar to speech processing. So when you're measuring this signal coming out of potentially 500 sensors in parallel, base calling would convert each one of those to its representative text string. That is, as you know, the submolecular structure of DNA is the 4 unique nucleotide molecules, the ACGT nucleobases. So you just want to figure out what this current measurement means in terms of those letters. And with that, you've got now what's called the a primary structure representation of the DNA, and then you would usually subject that to all sorts of ensuing bioinformatics, but it's not out of the question that even these rough measurements could give you some insight about the data. And certainly this is, in a sense, a form of compression. There's a lot of stuff here you can throw away. You don't need every single sample. This is, from most applications, this text representation is really all you want. And so how would you do that real-time base calling? So two general approaches to that would be both essentially stochastic detectors, an HMM base caller, so a hidden Markov model base caller, or you could now flex the more popular algorithms for this type of work, and that's you rely on your deep neural network approaches. And to give you guys a sense of the computational load, so this is if you want to go at real-time speed. So if you want to keep up at least with the current rate at which these little devices can actually output data. So if you're wanting to do a hidden Markov model implementation, you're looking at about 70 giga operations per second. That'll give you a conversion accuracy from that sampled waveform to text of about 60 to 70%. For deep neural networks, you're looking at about 4 times as much computational workload, but also better accuracy. And to give you a sense of what currently is kind of needed to get a real-time processing, this is, at least from my experience talking to researchers in the field, I haven't really dissected it, although I have sequenced with one of these devices, but I wasn't really paying attention to its real-time performance. In any case, to get what these researchers described as real-time conversion, that is, they were getting base called files popping out almost as soon as they were measuring with the device. It took a $25,000 machine, so they were running on a 24-core, 500 gigabyte RAM device. And also with that, there's not only a price and complexity cost, but the power consumption puts it far out of any reasonable embedded computing application. And the base calling algorithm itself, it's just a bunch of for loops, but in essence, what you've got is you're going to load your statistical model, then you're going to find the probability that the observation you made, this event is essentially means your measured data, belongs to a particular type of expected level, and then you do another calculation, which is just a multiplication of the degree of confidence you have in the value of your observation times what you've seen before, kind of. And this is just now you're just getting into a bunch of nested for loops. You've got to do this over all possible ways that the molecule, you could imagine, goes through the sensor. This is what this for loop accounts for. And then you've got to choose the option that's most likely. And then you've got to choose all the possible measurements that you think you can make on this device. And then finally, you've got to repeat this over all of the essentially letters that are within any one strand that you're measuring. And then you've got to repeat that over all of the channels. Like I said, this would be 500 in a little handheld unit today. So there's just a bunch of nested for loops. And in our case, oh yeah, so you're looking at about 30 billion iterations per second here. And bottom line is, in our case, what we want to put in our embedded system is aspects of these two inner loops. That's what we'd like our RISC-V chip to accelerate. This is just a nod to the fact that perhaps you don't necessarily need to embed your device. You could take these signals and just communicate them to some remote computing resource, so something in the cloud. Now, obviously, since you're not doing any processing on this data, you have to blindly send everything you measure at long remote distances. This gets kind of expensive, I think, not in terms of only direct economic cost, but obviously in terms of the power needed to maintain that communications just as a sanity check, I was looking at, I think these are right. If I wanted to do real-time base calling on the cloud with this data, on Amazon Web Services, you'd be paying about $5 an hour. So about $40 per genome. I'm not really sure about the cost trade-offs there, but I think they might still lean towards preference for some kind of a practical embedded device that gives you these letters inside the box. And okay, so this is just an example of what we've already done as far as acceleration goes. So we've looked at this problem with FPGAs. So we had, a Vertex 7 board plugged into a Intel Workstation's motherboard, and then we were able to stream the equivalent of measurements directly from the CPU to the FPGA and just see how fast we can go. So that worked out quite well, and we were encouraged that acceleration really has, or custom hardware acceleration really has a potential role for this application. So for instance, with that FPGA board, we were running about 500 times more energy efficiently than the CPU only, and reaching peak speeds of about 0.45 genomes per hour. So just to remind you, that little box can produce about 0.25 genomes per hour if it's running full tilt. And that was from a 250 megahertz clock. And altogether, a 6-watt power consumption, incremental power increase for this entire unit. When the CPU ran on its own, it required about 25 watts. Okay, so now we want to do the same, but in entirely ASIC form. So we don't just want an Intel CPU and an FPGA, we just like one chip. So whatever we did in the FPGA would go here, but now it'd be sitting right next to a RISC-V chip. And here's what we have so far. So we're looking at an open source RISC-V running an RV64 GISA. So that's obviously 64 bits, and it's got integer multiply and divide, and single and double precision floating point. The architecture, or the rocket that it's running on is available via Chipyard, which is again an open source SoC framework available from the Berkeley Architectures Research Group. And we also include a number of blocks which are not actually in this particular chip. This is just a raw RISC-V chip. It would have a bit of trouble communicating to the outside world, but it's got the key functionality to help it do that within the Encore here. You know, we haven't played around with any of these values. We're just kind of stepping through the tools so far, but the defaults that were available were 4 kilobyte instruction and data caches, which, as you can see, take up the majority of the space on this die, which is 22 nanometer fully depleted SOI from GlobalFoundries. But without any effort, at least in this picture here, towards customized memories, it was pretty good. Even in the triple slow corner, we were able to run this only at design compiler level, so not at after place and route at 500 megahertz. And the fast corners look pretty good, but in our implementations, we probably won't be able to run it this fast anyway. So as far as accelerating the RISC, there's a lot of open source help here that directly comes from the design of the RISC-V instruction set, which gives you custom instructions that allow you to communicate with the, that allow the rocket core to communicate with the base caller. In our particular case, command and control values are sent via one channel, and then data is exchanged between these two blocks through the L1D cache. In particular, we use the Rocket custom coprocessor instruction set to accomplish that. And just to give you a little bit more detail of the arrangement of that within the system. So the Rocket is a simple in-order 5-stage processor. And all the commit stuff happens at the very end in the write back stage. So it also doesn't give you any hazard problems because your accelerator instruction is the last one to commit. But again, this is probably room if you feel comfortable enough with customization. There's enough information in the open source stuff to move these blocks around. But we're just following the standard architecture to accomplish this. And these are some of the preliminary simulation results we've had, and it looks pretty good, although I have to amend this. This is just like the slides I submitted, so I figured I might as well not change them, but I think we misunderstood how many instructions took how many events. So I would say at the moment, we're probably barely, if 10 times more energy efficient than our FPGA example. But things are quite rough at the moment, but at least these numbers are correct up to synthesized simulations. So at 500 megahertz clocks with random vectors, the RISC-V alone in 22 nanometers was chewing up 50 milliwatts. And the other open source stuff that I alluded to was from the Bespoke Silicon group at Washington. So this is actually really important stuff that allows our core to communicate with the outside world. So it's one thing to build the IC, but in order to get a program into it and to be streaming data into it quickly from outside is actually feels a little bit more challenging right now. So another open source utility from this Bespoke Silicon group provides all sorts of I/O blocks written in System Verilog, in particular double data rate source synchronous communication that we can use to get this chip talking to the outside world. And so besides this Encore stuff, BSG also provides board level designs. So the way that this system is shaping up to look at the moment is we would have a Rocket sharing a daughter board with a gateway chip that's a Spartan 6. This Spartan 6 would be managing the power for the chip. It would also be providing the clocking, so there isn't any really advanced analog stuff on this particular version of the chip. And it's also a gateway to essentially the North Bridge, our memory system, and the PC. So this is low voltage TTL comms that's happening between the gateway and the Rocket on this right side. And via FMC, the gateway is talking to probably another FPGA, a Z board using LVDS, where we can leverage all sorts of Xilinx IP to do DRAM controllers. I guess that's not exactly open source at this level, but might be amenable to that. And I guess my time is up, but that's all I wanted to mention here on the open source stuff, the boards as well that we're looking at.
All right, thanks, Sebastian. That's very interesting. I appreciate you joining us today. We didn't see any questions come in over the chat box. Maybe flying over everyone's head on the DNA sequencing stuff. But certainly, I think you'll have generated lots of curiosity within at least our open source community on how we can help your project. So thanks for joining us today.